As fall turns to winter and temperatures drop below freezing, frost action begins damaging our roads, and the problem continues right through winter into spring. The resulting heaving, dips, cracks, potholes, and dislocated posts cost all of us money. They damage our vehicles, and repairing them consumes major portions of our highway budgets. Three factors work together to form ice that damages our roads: water in the soil, freezing temperatures, and frost-susceptible soils. Or, in more memorable terms, it's the 3 W's: water, winter, and wicking. To construct and maintain roads that minimize the effects of freezing and thawing, roadway officials need a clear understanding of frost action in soils. In a 1960s laboratory experiment, the U.S. Army Corps of Engineers Cold Regions Research and Engineering Laboratory demonstrated how frost action occurs. Researchers placed a soil sample in a clear plastic cylinder above a porous stone through which water was supplied. The soil is a type of New Hampshire silt known to be frost susceptible. A lead weight representing 6 inches of pavement was placed on top of the soil. 2 scales measured the amount of movement, or heave. One scale was attached to a cylinder, while the other was allowed to move freely with the weight on top. The soil sample was placed in a temperature-controlled cabinet to simulate early winter conditions. An insulated window in front of the cabinet allowed observation. Granulated cork insulated the soil, so only the top was exposed to the cold air. The bottom of the cabinet was maintained at a constant temperature of 38 degrees. This simulated the natural situation that soil freezes from the top down. The temperature was controlled so the soil sample would freeze at a slow rate, about 1/4 of an inch in depth per day. A time-lapse camera captured an image once every 4 minutes. Here's the resulting film. When speeded up, the activity of several weeks is compressed into a few minutes. 1 second on the watch equals about 1½ hours of real time. Now, water accumulates in the soil and freezes into formations called ice lenses. The frost front is where the ice lenses can first be observed. The scale attached to the weight on top moves up, showing that frost heave is occurring. In this laboratory experiment, water was fed into the soil by gravity, and the soil became saturated. In the field, the problem is usually with unsaturated soils where capillary action, or wicking, moves the water. The camera was repositioned as the frost front approached the bottom of the soil sample. The moisture content increased from 19% to 55%. The heaving observed was entirely due to the accumulation and expansion of the water in the soil as it was transformed into ice. The originally 6-inch high soil sample grew to 10 inches, a total heaving of almost 70% of the sample's initial height. The lenses in this experiment were fairly small and uniform in size. In other samples, larger lenses were observed. Here, 2 ice lenses extend all the way across a soil sample. The larger lens is 3/4 of an inch thick. In nature, lenses several inches thick are often found. This same frost action damages our roads. Just as in the laboratory experiment, when water is drawn into the soil and freezes, ice lenses begin to form from the top down. Because ice expands as it forms, the soil heaves upward, until first bumps and then cracks form in the pavement. And just as in the laboratory experiment, as long as water is available and the temperature is at or below freezing, ice lenses continue to form deeper and deeper in the soil layers, and the affected layers continue to move upward, causing more damage to the pavement. By the end of winter, we're all experiencing conditions caused by frost action. In the spring, the ice in the soil begins to thaw just as it froze, from the top down. So now, water in the base layer is trapped between the pavement surface above and the still frozen subgrade soil below. With nowhere to go, the extra water pulled in by capillary action during the freezing process saturates and weakens the base. Now, traffic loading damages the entire pavement structure. Frost action can also occur in a road constructed with a granular base over a subgrade that has high clay content. The water drains through the porous base, but stops at the less permeable subgrade. Over time, more and more water accumulates. Because the water can't penetrate the subgrade, it perches above the subgrade. As winter continues and freezing temperatures go deeper and deeper, the water freezes, expands upward, and damages the pavement surface layer above. A similar problem can occur where water in the base cannot drain to the sides because the water is constricted by curb and gutter, filled-in ditches, poor quality material on the shoulder, or other structures that contain the water like a bathtub. Over time, the water accumulates, freezes, and heaves the pavement upward, causing damage. Frost action can also lift almost anything embedded in soil that's above the frost line, such as foundation pilings, utility poles, and fence posts. We can see how that happens in this experiment where dowels represent pilings. A barely visible void appears beneath the larger dowel as it begins to lift. Now, the smaller dowel begins to lift. The void beneath the larger dowel fills with water. That softens the walls so they collapse inward. Other objects embedded in the soil can also be lifted. For example, in this experiment, an artificially colored rock was lifted 3 inches by frost action. In 2003, this Minnesota Local Road Research Board report provided more detail on how frost action occurs and showed how to avoid it. The report notes that frost damage is most likely to occur at transitions between roadway materials that differ in composition, consistency, and/or drainage characteristics. The report lists these types of soil that may be frost susceptible. It points out that all these types are fine-grained, have poor drainage characteristics, and tend to hold water. The groundwater that freezes to create frost heave can come from precipitation or nearby lakes, streams, swamps, or springs, and is more likely to cause a problem where there are natural or human-made swales, valleys, and cuts in the terrain that direct water toward the pavement. There are several effective methods for repairing frost-damaged pavements, or, better yet, for building new pavements to avoid frost damage in the first place. In all these methods, the key is to control the water. If water can be drained out of a material, prevented from entering the material, or prevented from freezing, that material will not be susceptible to frost action. These design methods fall into 4 categories. One is to improve the quality of the subgrade. For areas with non-uniform subgrade soils, the most comprehensive approach is to remove the frost-susceptible soil and replace it with non-frost-susceptible material. Many agencies require replacement material with no more than 5 or 6% fines. The material must be placed deep enough so frost is unlikely to penetrate to the materials underneath it. That depth will vary depending on local conditions. A less expensive approach is to blend non-frost susceptible material into existing frost-susceptible subgrade soil. This method reduces the occurrence of differential frost heave in the pavement by achieving greater consistency throughout the subgrade. A more expensive alternative is to blend a stabilizing additive such as fly ash, Portland cement, or a proprietary product into the existing frost-susceptible soil. These materials either harden the soil or prevent excess moisture accumulation so the soil resists frost action. The second method is to insulate a frost-susceptible subgrade from the upper pavement layers to inhibit the top-down advance of frost. This can be done by placing a layer of insulation 18 to 48 inches below the roadway surface. This depth is needed to prevent variable icing on the surfaces of adjacent pavement sections with different underlying structures. The third method provides a capillary break that prevents moisture from being wicked up from the subgrade into the base. This can be done in several ways. One is to place a 12 to 18 inch thick drainable base, also called a rock cap, between a frost-susceptible subgrade and the base layer. Agencies specify rock cap material as coarse, open-graded aggregate with a low limit on fines content. A fourth way to prevent frost damage is to drain water in the subgrade to the sides of the pavement structure where it can be diverted to ditches. or, in urban areas, to a storm drain system. This can be done by placing a geosynthetic composite between the base and subgrade layers. Proprietary products are available for this purpose that increase water flow because they promote wicking and draining action. Water can also be drained to the sides of a pavement structure by crowning the subgrade. If the subgrade is relatively impermeable and the overlying base material has been designed to accommodate drainage, water will drain off the upper surface of the subgrade. If the subgrade is somewhat permeable, it will absorb water until it's saturated, and then additional water will flow to the sides. Yet another way to move water to the sides of a pavement structure is to install perforated drain tile at the outer edges of an excavated subgrade. If the fines content of the base is not too high, gravity will drain water into the tile. As we've seen, frost action is a major cause of pavement damage. The three conditions needed to produce frost damage, water, winter, and wicking, exist in many parts of the world. And the damage caused by frost action is a major cost factor for public works agencies and for road users. But we've also shown that there are several ways to design pavements to resist damage from frost action. Since winter is unavoidable, the goal of all these methods is to focus on the water and the wicking. That can be done by improving the subgrade soil, insulating a frost-susceptible subgrade, creating a capillary break that prevents water from moving upward, or by moving water to the edges of a pavement structure. And designers can use combinations of these methods to provide extra assurance against frost damage. Given the cost of repairing frost-damaged pavements year after year, the old adage that an ounce of prevention is worth a pound of cure is good advice for pavement designers working in cold climates. For more information on all these methods, and for information on additional ways to construct and repair pavements to avoid frost damage, consult these resources.